Human speech is extremely non-stationary, with its acoustic and spectral variations shifting in a mere fraction of a second. When you add the pervasive broadband noise found in everyday environments, extracting reliable emotional cues from a vocal signal becomes a formidable mathematical problem. The industry standard for speech emotion recognition maps the audio as a raw spectrogram and feeds that entire image into a monolithic deep learning architecture, like a standard convolutional neural network. SER is a field of effective computing that classifies human emotional states directly from the acoustic properties of voice signals. This approach forces the network to process conflicting acoustic information simultaneously. A raw spectrogram overlays continuous tonal energy, the harmonics, and transient explosive noise, the percussives, in the exact same time-frequency space. This chart shows Russell's circumplex model, mapping emotional states onto a two-dimensional plane of physical arousal and valence. Both anger and happiness sit right next to each other in the top right quadrant. They share nearly identical macroacoustic properties, like increased volume and accelerated speech rates. Because the physical energy signatures are so similar, a monolithic neural network struggles to isolate the subtle spectro-temporal differences required to separate a joyful shout from an angry yell. The Dual-Decomposition Ensemble, or DDE-SER, solves this by splitting the signal before it reaches the neural network. It bridges one-dimensional adaptive frequency extraction with two-dimensional structural time-frequency mapping. Stacking multiple high-fidelity representations on top of each other creates massive computational overhead. The DDE-SER instead extracts strictly orthogonal effective cues, features that are mathematically independent from one another, to resolve class confusion without the bloat. The architecture begins by bifurcating the input. Branch A operates directly on the raw, one-dimensional speech waveform to capture frequency-based emotional shifts. It uses variational mode decomposition, or VMD. VMD is an adaptive, non-recursive filter bank that mathematically decomposes noisy, multi-component speech signals into discrete, band-limited intrinsic mode functions, effectively mitigating the mode mixing issues of older methods. The system frames this decomposition as an unconstrained saddle point problem, utilizing an augmented Lagrangian equation that balances data fidelity with a strict signal reconstraint constraint. To solve this equation, the alternate direction method of multipliers, or ADMM, iteratively updates these modes in the spectral domain using Wiener filtering. ADMM is an optimization algorithm that solves complex mathematical problems by breaking them into smaller, easier-to-solve subproblems. Normally, engineers must guess the optimal number of modes and the exact penalty factor. Overestimating duplicates the modes, while underestimating discards critical emotional data. To automate this, Branch A integrates VGG OptiVMD. This creates an autonomous feedback loop from the fully connected layers of the network to evaluate hyperparameter configurations and minimize categorical cross-entropy loss. This dynamic optimization searches a bounded grid to find the exact parameters needed to extract the ideal multidimensional feature tensor from the audio segment. The system strictly isolates distinct frequency bandwidths. Narrowband tonal shifts, like pitch inflections in sadness, are captured precisely without being muddied by overlapping frequencies. While Branch A focuses on frequency, Branch B executes simultaneously to target the two-dimensional morphological differences in the audio structures. Tonal emotional cues, such as drawn-out vowels, manifest as continuous horizontal lines in a spectrogram. Conversely, broadband transient noises, like the explosive consonants in anger, appear as sharp vertical ridges. Branch B applies orthogonal median filtering directly to the magnitude of the short-time Fourier transform. The short-time Fourier transform is a mathematical operation that determines the sinusoidal frequency and phase content of local sections of a signal as it changes over time. The system then computes Wiener-like soft masking matrices to strictly partition the complex spectrogram, cleanly separating the harmonic magnitude from the percussive magnitude. These two partitioned matrices are averaged and mapped onto the Mel scale. The Mel scale is a perceptual scale of pitches judged by listeners to be equal in distance from one another, aligning the data with mammalian auditory perception. A final logarithmic compression scales the dynamic range, generating a two-dimensional hybrid HP-MEL map. By physically separating the spectrogram structures, the network isolates explosive consonants from the underlying emotional pitches, completely avoiding the parameter bloat of larger attention networks. Both branches process their respective data through shared VGG16 convolutional bases, outputting flattened 2048-dimensional vectors that converge at the fusion layer. VGG16 is a standardized deep convolutional neural network architecture widely used for extracting high-level semantic features from images. Standard models linearly concatenate these vectors, which assumes both domains are equally informative for every emotional class. But broadband noise dominates an angry expression, while narrowband tonal shifts dominate a sad one. To solve this, the architecture uses a trainable gated attention mechanism. It passes the data through a sigmoid activation function to constrain the gating weights strictly between 0 and 1. These constrained attention scores act as intelligent informational filters, evaluating the incoming vectors from both the one-dimensional and two-dimensional pathways. The network applies a Hadamard multiplication, an element-wise product that selectively weights the most relevant orthogonal features from each branch. This multiplication explicitly zeroes out representational redundancy. If the network detects anger, it dynamically amplifies the percussive features and dampens the rest. This dynamic weighting grants the network the representational flexibility of a massive transformer model, but maintains a highly deterministic and computationally lightweight footprint. Deep learning architectures are highly prone to overfitting when trained on the limited, pristine acted speech corpora currently available to researchers. To combat this, the DDE-SER pipeline utilizes an in-place acoustic perturbation strategy. It systematically shifts the pitch of the original audio upward by 2 half-steps and injects dynamic white Gaussian noise. Standard blind oversampling simply duplicates identical hiles, which fails to introduce real acoustic variance. Injecting noise forces the convolutional layers to actively isolate emotional formants from ambient interference. The architecture was tested on the EMODB and RAFDS benchmark datasets using a strict Leave One Speaker Out or LOSO cross-validation protocol. LOSO is an evaluation method where a model is trained on all speakers except one, using that single held-out speaker exclusively to test accuracy. Random data splitting inherently leaks speaker-specific acoustic traits into the validation set. It falsely inflates predictive accuracy by allowing the model to memorize a specific actor's voice. By holding out an entire speaker's audio, the system proves it has learned generalized human emotional embeddings rather than memorizing individual speaker quirks. Under this strict protocol, the framework established robust overall accuracies of 74% on the EMODB dataset and 77% on the RAFDS dataset. The model achieved its highest recall rates on emotions like anger and sadness, correctly identifying sadness over 80% of the time. This success directly validates Branch A. The variational mode decomposition isolated the narrowband, continuous tonal energy that characterizes sadness, stripping away irrelevant frequencies. This chart shows the normalized confusion matrix for the EMODB dataset. While overall accuracy is high, specific bottlenecks remain in the high arousal quadrant. Looking at the happiness row, we see a severe misclassification skew. Happiness is erroneously predicted as anger in roughly 1/3 of instances. This specific crossover perfectly maps to the deep acoustic similarities predicted by Russell's circumplex model. High arousal states share identical physical energy, requiring even finer valence extraction to differentiate them. This chart shows the RAFDS dataset confusion matrix. Here, we see broad intraclass variance in the disgust row, where predictions disperse across sadness and anger. Because disgust can be expressed as cold or explosive, the network has to continuously reweight its fusion strategy. By simultaneously processing adaptive frequency modes and structural spectrograms, the DDE-SER framework provides a deterministic, computationally optimized solution. It successfully disentangles persistent emotional confusions, establishing a resilient standard for real-world affective computing.